Hello, this video is for Stat 210, Handout 10, Part B, and is going to cover pages 13 through 21. Okay, let's go ahead and get started then. So the data set that we're going to use for this handout is the vitamin intake data set. That has been provided in our Google folder here. Handout 10, Part B is just going to cover a second example of a paired t-test. Okay, let's go ahead and get started. Consider a study that was done here at Winona State. The following information was obtained from the study participants, and the study participants was WSU students. This study was actually a biology capstone project. So some of the information in the data set includes the gender, body mass index, and then we have several other variables. We have calories. We have calories actual here, as we can see. And that's the actual amount of calories that were taken in on that particular day. We also have calories DRI, which is just the daily recommended intake. So the students that did this project were able to calculate how many calories that particular person should have been taking in. And what they wanted to do was just simply compare the amount that was actually taken in against what should have been taken in, or against their DRI number. We have information on calories, vitamin A, vitamin C, calcium, and iron as well. But for Handout 10 Part B, we will just be looking at calories here. So the goal is to investigate the caloric intake to determine whether or not WSU students are taking in an appropriate amount of calories. So to do this, because each person has a different daily recommended intake, we are going to want to compute differences. So we're going to want to look at how far off was this first female away from their actual intake. The actual intake compared to the DRI. How far off are those two quantities? So here you can see that they're about 300 off. Down here, we have somebody that is supposed to be taking in about 1,750 calories. They only took in about 900. So this individual down here is way under what they should have been taking in. Okay, so let's go in Jump and compute that difference column. So as I said, in Jump, there's lots of different variables here. We have calories, vitamin A, vitamin C. So I'm just going to get rid of everything except for the calorie information. So I can just delete those out. Makes our data set a little bit more manageable. And the first thing I'm going to do is compute a difference column. So let's do that inside a Jump. Select Formula here. And then I'm going to compute the differences as actual minus the DRI here. So again, how the differences are computed, we have to know that so that we can interpret things correctly. And again, the way that I've computed them here is actual minus the DRI. Say OK. And now I have my difference column. I'm going to use this column for my analysis. So analyze distribution. The differences is what I'm analyzing. Turn that on its side. We can see that the average is about minus 350 or 346. The average is minus or negative. It just means that for these people, there's actually 71 people in this study. They're taking in about 350 less calories than they should be. So again, the differences were computed as actual minus DRI. Page 14 here includes the output. I also created the dot plot. There's two questions here on the bottom of page 14 that you can answer. So go ahead and hit pause to the video and try to answer those questions. Okay. Before we go forward with the test, we should check the normality assumption. And again, I do that from the red drop-down menu inside of Jump. I can just ask for the normal quantile plot. And what we're looking for is that the dots should be between these bands, which they are. So the normality assumption is okay. We can proceed with our t-test. My research question here, is there a difference on average in the amount of calories actually taken in a person's daily recommended intake? We have that stated in words and also with our parameter here. So again, what we are testing is the average difference, equal to 0 against not equal to 0. We will use a 5% error rate. To complete this test in Jump, I just need to select Test Mean from the drop-down menu and specify the hypothesized value here. The value that goes in this box right here is the same one that is in the H0. This is almost always going to be 0 for a paired t-test. We're almost always interested in just determining whether or not there is a difference. I'm not going to cover the nonparametric test in this class, but the Wilcoxon signed rank test is a test that is available and should be used when you have concerns with the normality assumption. So up here, if these dots start to drift outside of these bands, or if your data is skewed in one direction or another, we really should not be using the t-test. But what we can be using in its place is the Wilcoxon signed rank test. You would simply select that box and it would return a p-value for that test. Again, the Wilcoxon signed rank test is a nonparametric test and should be used when you have problems with normality in your data. Here we do not have problems with normality, so I will just stick to the standard t-test. Here's all of our output again. I have my actual estimate, which is just the sample average. I have my standard deviation, and then I have that standard error mean. The standard error mean, again, is the standard deviation of the average over repeated sampling. That's what's going to go into the denominator of the test statistic. So my test statistic here is just the actual estimate minus 0, divide by the standard error for the mean. I get about -6 here. So on my schematic here, on my t-distribution, one standard deviation is about 60. So starting here at 0, I have to go down about 6 standard deviations to get to my data value, or to get to my average of -346. I am 6 standard deviations away from 0. That's substantial. That's a lot. Anything more than 2 would be considered unusual. If we use the p-value approach here, the p-value that we're going to want to be selecting is the one for the two-tailed here, prob bigger than absolute t. That is less than 0.05, so I have enough evidence for the research question, and I can go ahead and make my final statement, again using layman's language here. Make sure and include the p-value at the end of that statement. Okay, let's move on to the 95% confidence interval. The 95% confidence interval has the following form. We need to compute or obtain the IC value, or the interval coefficient for that interval. Again, that t-distribution is indexed by its degrees of freedom, which is going to be 70 here. If we go back up and look at our output, I had 70 degrees of freedom. There were 71 observations, so the degrees of freedom value is going to be 70 here. If I go to that applet, I would just plug in the degrees of freedom at 70. I want to select the 2 times p bigger than absolute x, and I'm using a 95% in the middle, which is going to give me 5% on the outside. So we can see that the interval coefficient here is 1.99. This value is always going to be pretty close to 2. Okay, so if you don't want to go through the work to obtain the interval coefficient, some people just use 2 in that for the IC value. It's not that hard to get the IC value, so I would encourage you to use and apt to obtain that value. Here's what the 95% confidence interval looks like. We can see from our output it goes from minus 231 down to minus 461. Recall that the average was at minus 350 or so. So right here at the average at minus 350. And there's going to be variation below and above that quantity. The margin of error here is computed by this part there. That's just the IC times the standard error, which is about 115. The interpretation here is we are 95% certain that for a WSU student, on average, their actual caloric intake will be about 230 up to 460 less than their daily recommended intake. If we just shorten that a little, we can just say for WSU students, the actual caloric intake tends to be about 350 plus or minus 115 below their daily recommended intake. Now, because I looked at what would happen over repeated samples, I can extend my statement here to WSU students, not just the students that participated in the study, but WSU students in general. So because I took into consideration what would happen to that average over repeated sampling, I'm able to expand my scope of inference to not just these 71 people, but WSU students in general. Okay, just some additional details regarding t-tests. There is a connection, certainly, between the 95% confidence intervals and the decisions from our test. So in the example that we looked at above, the interval was completely negative. It did not include any positive values, or it did not capture 0. It stayed negative. That's going to tell me that my p-value is going to be less than 0.05. So for a test of differences, for a two-sided test of differences, I would just want to know, is there a difference? Well, if it stays away from 0, if the 95% confidence interval stays away from 0, it does not capture 0, then there's going to be a difference. So in this case here, I know that the p-value is going to be less than 0.05. And I know I can say that I have enough evidence that a difference exists. The confidence interval actually gives me endpoints to tell me or to communicate how much of a difference exists between the two. Here's another one where the interval is completely positive. Okay. The 95% confidence interval is positive and does not capture 0 again, indicating that, again, on average, a difference exists. It does not capture 0. The third interval here does capture 0. So in this case, I am not going to have enough evidence to say a difference exists, because 0 is a likely value, and 0 indicates that there's no difference. That value is somewhat likely in this interval. So in this case, I do not have enough evidence to say a difference exists. So I can actually look at a 95% confidence interval and make a decision about my test by just understanding where that interval is relative to 0. In practice, one-sided paired t-tests are less common. So here I've taken the original research question, which just asked, is there a difference, and changed it to the following. So the one-sided research question would be something like this. Is there statistical evidence to say, on average, that WSU students are undereating? In other words, I would like to know whether or not that average stays below 0. So this certainly has a direction associated with it. This is going to be a one-sided left test, so I'm going to want to use this p-value on the bottom, the prob less than t there. It's still going to be less than 0.05, so I am going to be able to say that there is enough evidence to say that WSU students are undereating. Now, the appropriate 95% confidence interval is also going to be one-sided. For a one-sided left test, again, what I'm interested in is determining whether or not the average, over repeated sampling, is going to stay below 0. Now that's going to happen when the upper endpoint of the 95% confidence interval stays below 0. So for a one-sided left test, what I actually am interested in the interval is the upper endpoint to make sure that it's going to stay below 0. The interpretation of this one-sided 95% confidence interval would be that we are 95% certain that on average, the difference between actual and daily recommended intake will be at least 250 calories. So kind of the best case scenario would be a difference of 250. Again, WSU students are under-eating by at least 250 calories. To get the 95% confidence interval in JUMP, for the one-sided interval, from my drop-down menu, I'm going to select Confidence Interval, Other. I'm going to want to select, for a one-sided left test, I want to select the upper limit. Click OK, and that output will be given to you by JUMP. Okay, that does it for handout number 10, Part B, pages 13 through 21. Thank you.